So in this video, we are going to have a mass of some kind, an object, starting from rest, and it's going to fall down some known distance, so we know how far it's falling, and we want to find what is its final velocity after it falls that distance. So this looks like a kinematics problem, really, but now that we know about energy, we can solve it using energy. This video is for if you have learned about potential energy. So now that you know potential energy, we are going to use what is called the conservation of energy. You may know it as the work done by non-conservative forces is equal to the change in energy. I prefer to break change in energy into final minus initial and rearrange the equation so that it looks like this. Final energy is equal to initial energy plus the work done by non-conservative forces. I'm not sure why, but this is just how I like to think about it. Okay, so we need to identify the energies in this problem. We have the final energy. Well, it could have potential gravitational energy, and it could have kinetic energy. Right, gravity is involved here because we're changing height. Okay, we're rising or falling, so gravity is playing a role. And that will be equal to the final, or the initial gravitational potential energy plus the initial kinetic energy plus any work done by non-conservative forces. So non-conservative forces are things like friction, someone pushing, stuff like that, right? Okay, so recall that definition for these things. Kinetic energy is equal to 1/2 mv squared. Potential gravitational energy is equal to mgh. And work in general is the force doing the work times the distance it's doing work times the cosine of the angle between the force and displacement. Okay, so if we started from rest, our initial velocity was 0. So since velocity is in kinetic energy, the kinetic energy was 0 initially. So let's zero that out. All right. Now, if we call this the height of 0, as in kind of like that's my origin down there, then in the end, in the final picture here, it's at a height of 0. So potential energy has height in it. If the height is 0, then the potential energy is 0. So this is our final case. So in the end, we have a potential energy of 0 because the height was 0. Right, and here because the velocity was 0. Okay, so we've simplified it a little bit. Now let's think about the work done by non-conservative forces. Now we're ignoring wind resistance like we usually do. There's no friction involved. There's no person pushing on this thing, so there are no non-conservative forces in this problem. Okay, so rewriting it, I have simplified it to kinetic energy is equal to the potential. The final kinetic energy is equal to the initial potential energy. Okay, well, kinetic energy is 1/2 mv squared. Potential energy is mgh, right? And that is what this height is here, right? I called it h. All right. We don't know the mass, but that's okay. All we knew was the height. It's okay that we don't know the mass because we can divide both sides by m and solve for v. So we're going to get that v is equal to the square root of 2gh. And that's exactly what we would have gotten if we used kinematic methods to solve this problem. This is much easier, I think. So that's our answer.